Today is the 20th. We are going to finish up capacitors today. We are scheduled to have a test over chapters 28 and 29 on Tuesday. Okay. You may be sad to know or disappointed, I don't know, to know that I did not get a problem set written for this one. I apologize for that. So if you want more problems, I can make copies of problems from another book. I just didn't get a chance to pull them out because my daughter's birthday was yesterday, and that took precedence over writing a problem set for you. I know, right?
She's so old.
How rude is that? She is.
How old is she now?
Two. How old are you, Miriam?
She's so old
2.
without actually knowing her age.
Well, but
No, I know it is. Every year, every birthday you have makes you so old.
yeah.
Yeah.
So,
But I also really want to make sure that you are aware of what's happening then the rest of the week next week. So next Tuesday is the 24th. We're going to test. The 26th, the 25th, we're going to meet for lab, right? After school. So that's the Wednesday. Is everybody okay with that? You know that that's happening. Jack may or may not be alive that day, but he will be here, or he'll make some other arrangement with me to do it. You can do it by yourself another time. Just let me know when. But we're going to lab on the 25th. On Thursday the 26th, I'm going to answer questions, go over anything that you want to know from chapters 30 and 31. Okay? And then on Monday the 2nd, we're going to test over chapters 30 and 31. Does that make sense to everybody? So 30 and 31, thanks, are over Ohm's law, series and parallel circuits, Kirchhoff's law. We'll talk more about Kirchhoff's law at lab on Wednesday.
You should keep all of Gabe's passes in the box.
I was thinking about and Logan, they have tons, right? But I just want to make sure that this makes sense to you so you know what's coming, because it's going to be kind of a back-to-back kind of deal. Questions about this stuff right now? And then we have a lab on the 11th. This one will be an early, it says evening, but it will be an early lab, probably right after school if we can do that, because I have conferences that night. Does that make sense to everybody? So I'll tell you more details about the time on that. And if you need to come in later to do it, you can, I suppose. I just won't be available to answer questions. Okay.
So are we gonna start like a new unit?
So
right after that, then.
So on the 2nd, we're gonna test over series and parallel stuff. We're gonna test over circuits.
Yeah.
But this lab actually goes with this. We just didn't have time to do it.
Okay.
So there won't be any RC circuits on this test.
Okay.
But I will give you a take-home free response question that will be due right before break.
Okay.
And then on the 4th, the 4th and the 6th and whatever those next days are, we will start magnetism.
Okay.
Yeah. I just haven't given you that new calendar.
Okay.
Yeah. Other questions? Are we okay?
This is gonna be a rapid 2 weeks for me.
You can do it. And then it'll be spring break, and that'll be a beautiful
And I'll
moment.
But I
never
have
return to
7
school.
scholarships to write stuff.
I know. You can do it, though. Got to get it through, and then it'll be spring break. And then it's all going to go really fast, and you won't even know what happened.
I'll just
Terrible.
cry for the next
AP
month.
comes,
Just to let it all out.
freaking out, and it's terrible, and it's a disaster.
And then it'll be summer, and that'll be
It's a
great.
train wreck.
And then you come back next year.
I just won't come back after spring break.
At all.
You're just going to, that's the end of it?
No one will
Dropping
really
out,
make
we're
it.
done.
I'll
Okay.
say that.
My swim coach wants me to swim with the regional.
All right.
I get back from Germany.
I would encourage you to get some notes out. Let's go ahead and get started. So we've only got a couple sections from 29 to finish up. I don't think that it should be super hard. And then I do have your tests to give you back. Was that what you're going to ask about? Yeah. I have them right here. I'll give them back to you right after we do this. I figured we'd get this done first, and then we can do tests. Yep. All right, here we go. So we've been talking about capacitors. I'm talking about how they work, how we can put them in combinations. The whole point of having a capacitor is that we can store energy in them. That's what we want to talk about now. So let's talk about the energy stored in a capacitor. Okay? So if we think about it from just a very, very basic perspective, in order to charge a capacitor, the battery must do work, right? The battery does work to put charge there, to increase the potential energy of the capacitor, and we can quantify that. Du equals dq, whoops, I meant to put a d in front of that q, times delta V. Okay. And if you just take the d's off, then that's the definition, right, of how we get to potential. And if we write that in terms of a capacitor, then we can say that that's dq times q over c. That's the definition for capacitance, or a way to write the definition for capacitance. From there, we can then actually find that energy by integrating. So we can say that the energy stored in a capacitor is equal to the integral of, oops, well, I guess I'm going to pull that 1 over c out, sorry. It's a good thing that you take notes in pencil because, I change my mind a lot too. Integral of q dq, it's kind of fun to say, from no charge to the amount of charge that's going to be placed on that capacitor in total. We can all do that integral, right? That's not a big scary one. Don't make that face, Jack. I bet you can do it.
Total charge squared
Over.
2 times capacitance.
Yeah. Oops. Is that okay with everybody? From there, you can also write this, remembering our definition for voltage. We can also write this, the total amount of energy that is stored equals 1/2 C delta V squared. Is that okay? We're using, again, that delta V equals Q over C there.
That looks an awful lot like all the other types of energy.
Right, isn't that interesting? It's a little bit weird, right? 1/2 mv squared, 1/2 kx squared. They many of them, right? They take all kinds of, or they all take kind of the same form.
1/2 I omega squared.
They just keep going, right? It just,
That's like the mass of the thing, like.
well, yeah. So I don't know that I would say that it's the mass.
It's the moment of
Because you don't want to go there. But it is kind of nice to know that the form is very similar. So you can kind of, as you're getting those in your head and trying to kind of get those organized in your brain, you can be aware that that form is going to look very similar for many, many of them. Okay? We've been talking about this stored energy. Why are we even talking about capacitors? Why would you want to use a capacitor when you have a perfectly good battery? What's so cool about a capacitor?
You can charge and discharge it whenever you want.
You can charge and discharge it whenever you want? Yeah, I suppose.
Through resistors and things.
Okay, so you can maybe control.
Control flow of electricity.
You can control it. The other.
What?
Yeah. Oh my gosh, right? You can also control how fast the discharge happens.
You can use them
With
extra batteries, like when ICs turn on.
Yes, so you certainly can't. You can use them kind of like extra batteries, but even more so, the nice thing about a capacitor, I can't remember if we did this with your accelerated physics classes or not. When you took accelerated physics, did we get to dissect cameras? Do you remember this? Did any of you get to dissect a camera? Okay, so here, let me go back and get a camera. I've got some in my back room. But right now we're not going to, because I want to make sure we do the material first.
We could just be in your room during conferences, just like flashes going on.
Woo! Right? So I used to do this really regularly, and then the amount of time and what we covered in accelerated physics changed a little bit. So we get these cameras, right? Like, and part of the problem is that few people use these anymore, so they don't have as many. Like, I used to be able to just go to Dolls and be like, "Hey, will you give me all your cameras?" And they're like, "Yeah!" So they just give me them all, and it was great. But they don't have them as many
Online
anymore.
ordering.
Right, but I don't want to buy them.
Oh, you just want to.
I want the ones after the film has been taken out. What I want to do is to take the rest of it apart.
Oh.
Okay? So when you take it apart, you can see there's like, so a lot of it's interesting in that there are are lenses, and there are mechanical things, right? There are like gears and things like that. But there's also a little tiny circuit board on there, okay? And that little tiny circuit board, really the only thing it controls is the flash, okay? Everything else is mechanical, okay? It's got little gears and it's got little levers and things like that that make everything happen. So like when you hit the shutter button, that's all mechanical, okay? When you wind the film, that's all mechanical, okay? All of that is mechanical. The thing that isn't is, and I don't even know if these are going anymore, but is the flash, okay? The flash uses a capacitor. The flash uses a capacitor. Why? What does a camera flash do? It flashes. It what?
It's like one quick bright flash.
Really bright, really fast, right? And we want all of that energy to be released right now. So the way that it works, have you guys all used a camera like this at some point in your life?
Yes.
I wonder like what year when I asked that, people would be like, I don't know what you're talking about.
This year.
Do you think like my 9th graders would say that? Like, I don't know what you're talking about. So when you're going to use these cameras, the first thing you have to do, you can't just take a picture and expect the flash to turn on, right? You have to hit the little button on the front. So if we draw this picture, it's going to make some like sound, right? And what is that sound?
Like the
Capacitor
fear and
It's-
anticipation.
It is not the fear or anticipation. It is the capacitor charging. Yeah, so
It's the bomb needing to be diffused.
storing.
That's what it sounds like.
Why does that make a sound?
I don't know. To be honest, off the top of my head, I can't tell you. I'm going to write this down from a capacitor.
Because it's not 100% efficient.
Well, certainly it is, but I don't know specifically why it makes that high-pitched sound, is what I mean. Storing and releasing energy from the capacitor in it's just getting an attitude here. In a disposable camera. Flash. Okay, so the way that it works, you've got a battery. There's just a AA battery, AA battery in there, and then you've got some switches. And when you hit the button that makes that really high-pitched sound and that charges a capacitor, the button that you're hitting is this switch right here. Okay? So you hit that switch, and then that capacitor is charging up, right? And then that little light starts to flash, right? Okay? So there's a little like bit of a circuit there with some logic that says once the capacitor is fully charged, then make that little LED flash. Right?
Capacitor's not sucking all the, like, when the capacitor's fully charged, it's not drawing any
Any
power.
current anymore, right?
any current.
Exactly.
So then you can just have another branch that just
Right,
has the-
right. There has to be a little logic gate in there that tells it to do that, though. Yeah, yeah,
Really?
yeah. I think so. Then, so after you've charged that capacitor, then you let go, right? You don't have to hold this down forever. You just let go, and then it flash, and it's ready to go. And then you've got your light bulb.
These are the really good story anything over like big clanging. God.
Dang it, I did not look.
Okay? And this switch right here is connected to your shutter switch. So when you click the shutter switch down, then not only does the shutter open and close quickly so that light goes into the film, or onto the film, I should say, but also it goes to the flash bulb. And because all of the energy is just coming from that capacitor to the light bulb, that discharge is going to happen really, really fast. And because the capacitor is high enough, or the capacitance is high enough, I should say, and there's enough charge on there, there's going to be a whole lot of light that's going to come out the light bulb. Does that make sense?
Yeah.
Okay. So that is why we care. Now, the book kind of takes that one step further and says, okay, well, where, like physically, where is the energy stored? So if you think about like with a spring, the energy is stored in the material that the spring is made of as it is stretched. Does that make sense? Okay, so as that thing is stretched, it wants to go back to its normal state, and that is where the potential energy is stored. Where in a capacitor is the energy stored?
Plates.
What's that?
Some of the charge is stored on the plates.
So the charge is stored on the plates. Where is the energy stored, though?
In the dielectric.
We're not there yet. So there is no because and
in between the plates?
what's in between the plates?
Nothing.
Not nothing though, because once
Now
well, if
there's
it's
nothing
not,
between
hold on.
An electric field.
Yeah. Okay. So here's the thing, friends, and I want you to get this. This is important. Even if there is a vacuum in between the plates, because we're almost to dielectric, so AJ can finally be happy, but we're not there yet. So we've still got a vacuum in between these plates. Jack is rolling his eyes about something, but anyway.
I'm not sure AJ's ever happy.
AJ and Gabe are always a few steps ahead.
Well, whatever. Then I'm just
Ignore
trying
the
to
young
shush
kids.
him.
Additional electronics.
Jack is off the-
What I want you to realize is that the energy has to be stored somewhere. The charge is stored on the plates. The energy is not stored on the plates. The energy is stored between the plates in the vacuum when a what is established?
The field.
An electric field. Yes. So the energy is stored in the E field that's established. Okay? So we can take this one step further and just kind of figure out how to quantify that, how to write that down. So we know that the energy stored in a capacitor is 1/2 C delta V squared. Okay? We also know that delta V is equal to E times D, and C is equal to epsilon naught A over D. So we're just kind of pulling all these equations out. We're going to push them together and see what happens. So if we take this first one, we're going to say the potential energy is equal to 1/2. Instead of saying C, I'm going to write down the physical quantity that is the capacitance, epsilon naught A over D. Okay, that's what we defined. I think we defined that last time, didn't we? That it was based on the physical specifications of the capacitor itself. Okay, and then instead of writing delta V, I'm going to write this as E squared D squared. Okay, and we can simplify that a little bit by getting rid of a D, it looks like. And so I can write this as 1/2 epsilon naught times A times D. What's the A? The area of the plates, right? And what's D?
Wait, would it be the area of both the plates or just one of the plates?
It's the overlapped area.
Oh.
So it's not like the area of this one plus the area. It's like that overlapped space. Yep,
But
yep.
typically aren't the problem like they're the same.
Right, right. So I'll show you in just a second that sometimes in electronics you will have opportunities, just give me a minute, to change the areas, and that changes the capacitance, and then by doing that you can change voltages and use that for helpful things. What's up?
Can I borrow Jack Logs for just a minute?
I suppose.
Thank you.
Here's the thing. And then A, you said, is the distance between the plates, right? So really this thing is like the what? What is that? The area between the plates
Like the physical character.
times the volume. It's the volume that is in that space. Yeah. So that's like the volume set up between those plates times E squared. Okay? We sometimes will talk about this in terms of like the energy density. Okay?
I think of trains. Okay.
It's, yeah, when the trains go by then. It's a beautiful
We're all
thing.
gonna die. It's like that little sound. It's like that little indicator. You're just things aren't gonna happen.
Very
Yeah.
pessimistic today there, Teresa, my friend. I don't know.
Just like this entire month. Hence why I did not write the optimist essay that is due today, because I'm not an optimist.
God, yeah, same. I'm like, I
Okay.
I am a realist.
So the energy stored is equal to U sub C divided by the volume okay, which is equal to epsilon naught E squared over 2. This is called the energy density of the electric field. Have a good one. You made it. It's nice to see you.
How was spring break?
Did you have a good spring break?
Yeah. Okay.
I went to Cancun.
Dielectrics.
Dielectrics. Yes. All right. Now Jack's like, finally we can get A data.
Except there wasn't something like that.
Oh, I'm sorry. Why not? What's your matter? Ah. You want the end of this one? Like that? There you go.
Well, you don't have the of electric field written, so.
Don't want any confusion. All right, now we good?
Wait, why is it E squared?
Because this is E squared
Which is equal what?
here, which is because the V was squared. So okay, let me back up for just a second. With a different color, yellow. So U sub C divided by the volume is called the energy density.
Okay.
Is that okay?
Is that volume for V? Oh, that makes
Yes.
sense. Okay.
Yes.
There's too many V's.
Yes.
Okay.
There are too many V's. Let me
Okay.
be really clear. That's volume.
Okay.
That's the energy density between the two plates.
Mm-hmm.
Of an electric field.
Energy density of an electric field between the plates of a parallel plate capacitor. That's a lot of prepositional phrases there. But then you know what it is. All right.
I know.
Are we ready?
Kasuga's name was even on it. Or I think, I don't know.
I don't think so, but maybe. All right, here we go.
It says Lindsay K, so we all just assumed.
Hi. You just set it right there.
Right.
Yep, perfect.
She's back.
All right, here we go. So the first thing in my notes says, so far all the capacitors have been two parallel plates separated by a vacuum, right? If we think about that, the charge, when we charge the capacitor, okay, when we do that, we know that delta V sub C is equal to delta V of the battery. And we know that the charge on the capacitor is equal to the capacitance, and I'm going to call that C naught now. So that's the capacitance of a capacitor with a vacuum in between, okay, times delta V sub C. Okay? We know that there's an electric field established between the plates. Okay. So I'm going to take that capacitor. I've got it. Oops, probably should draw a capacitor in there. So there it goes. I close the switch. I charge it up, and then I open the switch back up. So now I've got a charged capacitor, okay, disconnected from the battery, and now I'm going to put some sort of material in between the two plates. Okay? What's that? It's kind of like a sandwich. Yes. Somebody's hungry. Didn't have enough breakfast this morning. I don't know.
I'm always hungry.
That's after it's charged.
So it's already been charged up. So I'm just kind of like walking you through what's going to happen here. Is there going to be any change in the amount of charge on each of the plates? No.
Wait. What are we saying again?
I'm putting some sort of insulator in between the two plates.
Okay, yeah.
So I'm going to put some paper or some water, or I really always wanted to do a lab with some Jell-O. I think that would be kind of interesting. I don't know what the dielectric constant of Jell-O is. You're going to put some sort of insulating material, so not a conductor, right?
H gel, yes.
or put some sort of insulator in between those two plates. When I do that, again, it's unconnected from the battery. Is the amount of charge on the plates going to change? No. No. So there's no change, and that's really important to remember. No change in the charge on the plates. Okay? But if I took a voltmeter, you guys all know how to use a voltmeter now. If I take a voltmeter and I read the voltage across this capacitor, we would find that the voltage of the capacitor is no longer equal to the voltage of the battery. It has now fallen. Okay? The voltage has changed. And by extension then, does it make sense that I can say that the capacitance has changed? Is that okay with everybody?
Yeah. The charge is the same.
Right. So just by putting this weird insulator in here, let me just say one more thing and then I'll answer your question. By putting this weird insulator thing in, we are physically making changes to the capacitance of the capacitor. Go.
Does that mean that you get the capacitance for sure went up?
Say that louder. I can't hear you, honey.
For sure the capacitance went up based on the equation above. With the voltage decrease, capacitance.
Right.
Is that what it's implying?
Yes.
It always goes up then?
Yes.
Okay.
Yes. And we're going to talk about why right now. Okay. So I've got some pictures. These are just from your book. I just liked them and thought I would share them with you. The scans didn't work super well, but we can get out of it what we need. So the reason that this happens, even an insulator, any material you know is filled with charged particles, right? Everything is filled with charged particles, okay? AJ, would you not
Yes.
mess with my camera anymore? Like, just put it away. Thanks. We'll play with it later. Thank you. Okay, so anything is made of charged particles, okay? And when I put that insulator in this electric field, it's going to cause those charged particles to polarize. Does that make sense? It's going to polarize in the direction of the electric field. Now, this didn't scan very well, but let me tell you what's going on here. Or actually, let me have you tell me what's going on since we can't really see it. So in this picture, we've got electric field that's pointing to the left. So each of these little things here is a polarized piece of the insulator. Tell me what is where.
Positives left and negatives right.
The positives are over here, right? Can you guys see that? Not really.
I mean, sort of.
Kind of. So if it's like that, I'm just going to make it a little bit bigger. The positive's on that side, the negative is on that side. Is that okay? Does that make sense to everybody? Okay. So the molecules are going to become polarized. Some materials are more easily polarized than others. That means that some materials work better, and we'll talk about what that means in just a second. When they become polarized, they align with the electric field. Okay? Here's the fun thing, is that the polarized insulator then acts as two sheets of charge. So really, it looks like there's a bunch of positive charge hanging out over here. Are you with me there? And there's a bunch of negative charge over here. Okay? And because you've got a bunch of positive charge over there and a bunch of negative charge over there, it is as if there is an electric field, are you with me there, inside this thing. And I think I have another picture down here. We'll take a look and see if we can. So this is a picture of like the same thing, but then just without the little insulators, or without the little polarized pieces. So you've got your positive over here. And your negative over here. Which means that you have an electric field facing the other direction. So the electric field that was from the capacitor is facing the right, or excuse me, facing the left. The electric field that's established inside that dielectric, where does that word come from? Right. Di means two, right? So we're talking about something that is creating a second electric field. Okay? We've got this induced charge, this extra electric field that now points in this direction. So that means that the resulting electric field in that space is the electric field pre-dielectric. So that little sub-zero just means in the vacuum, okay? Plus the electric field that's induced in the dielectric. And that gives us an electric field that is less than the original. Because, to be very clear, this is going in the positive direction, this one's going in the negative direction. I added them because they have vector hats on top. So it's okay to add them that way.
What's with the
E sub 0?
No.
Or
not
E equals 0
equals
out there. Let me read this carefully and make sure. Can be represented by two sheets of da-da-da. I think that this was just saying if there was nothing out there. Yeah. I think. Let me make sure that I'm reading that correctly based on. That's how I would interpret that. Oh, I think what it's saying is that the induced electric field is only created inside the dielectric, not outside of it. Yeah.
So it doesn't project.
No. Is that like outside? Is that what you're saying?
Yeah.
No. Just on the inside. Right. Exactly. Same deal. Okay. Is that okay? Does that make sense so far? So what does this look like? In the bag that is labeled capacitors, I wanted to show you a couple of things. We determined that this wire isn't good. That's why it didn't work. So I just thought I'd share that with you. That's why the demo didn't work before. Let me show you a couple of things
Did we
here
get the
quick.
demo again?
What's that?
Did we get the demo this time?
No, because it's broken. We need to buy a new one.
Oh.
Ready to keep going? So that's how a dielectric works. It's pretty straightforward in function. When we want to actually start, like as an electrical engineer, if you're trying to actually figure out how to quantify the difference in electric field, the way that we do that.
That's my ride.
You're just ready to get out of here, aren't you?
So where were you again?
Cancun.
Yeah, all the way to Cancun.
I
Pulling
don't
the
go
hobo
anywhere
thing?
for spring break. I go to my room and sit there.
Not judging.
Cancun.
All right.
Band next year, we're going to Florida.
Okay. So to quantify the difference in the electric field, we use the Greek letter kappa. I find that I put little lines on the top and bottom there just so that I remember that it's a kappa and not a K and I don't get confused. That's what I do. Whatever you need to do to make it work for you is fine. That's just how I write it. That's not like convention. It's just that's.
Is there a convention?
I've
Or you
not
just know that it's Kappa.
I've not ever heard one. That doesn't mean that there isn't.
Okay.
Is that fair?
Yeah.
Yeah. Kappa is not a Greek letter that we use a lot. So, yeah. Anyway, kappa is defined as the E naught, so the electric field that is established with a vacuum.
Okay.
Yep. Divided by the electric field with the dielectric. Okay? So this is the factor by which the dielectric weakens the E field. Now, I guess we didn't really say this. Why do you want to weaken the electric field?
I believe that was the next question.
What's that? That was your next question?
Yeah.
Okay, so that's my question too. Why would you want to weaken the electric field?
Because you don't want to overload something, maybe?
Well, but if we just didn't want to overload stuff, I mean, I think there are other ways we can.
Capacitor.
So if we think about what we're talking about here, oops, I want to go back to the other page. I have this situation where I just put a dielectric in and it changed the voltage, right? The voltage is now much lower. You remember this picture we drew earlier, right? The voltage is much lower than it was originally. So now let's say that I put this dielectric in and then I close this switch again. What's going to happen?
The charge is going to go onto that plate some more.
Some more, right? So, okay, so let's back up here for just a second. If I have a capacitor with no dielectric in it, okay, and I close this switch to charge the capacitor, at the end, I know that the voltage across this and the voltage across this are the same. If I have a dielectric in here, now the voltage is different, right? Which means that if I close this switch, this and this don't equal each other anymore. Are you with me there? If they don't equal each other,
More charge gives
more charge. More charge, more
capacitance.
capacitance, more stored energy. So by increasing, or let me back up, by decreasing the electric field that's established,
You can hold more charge.
I can put more charge on there, and if we take that one step backwards again to the energy that's stored, I can now store more charge because my capacitance is going to be bigger and my voltage is going to be bigger. Do you see what I'm saying? I'm going to make...
Won't the voltage be the same though, because it's always going to be the same as that of the battery?
Eventually, yeah. Yeah.
Oh, okay.
Yeah, but do you see, like, there's a difference there.
Yeah.
The amount that I can charge it to, yes.
Right, yeah.
Are you okay? You look a little perplexed.
I followed you up until like you were like relating it back to the equation.
To this equation?
Yeah.
After
Okay.
she puts the dielectric in and closes the switch,
Mhm.
and then more charge accumulates because the capacitance is higher and the voltage is lower, right? So then more charge accumulates, bringing the voltage back up to match that of the battery.
Okay, I feel like I need another explanation about that one more time then.
Okay, let me take one more step here.
Yeah, yeah.
And then I think it'll be better. Okay, so are you okay with that statement right there?
Yeah.
Okay, so then if we, let me write some more stuff down. Delta V sub C is equal to E times D. Do you agree with that?
Yeah.
Voltage is equal to E times D, and that's not really a dot. I just get in the habit of writing a dot, but I don't mean it that way. But E is really E naught over kappa times D. Is that okay?
Yeah.
Which is really delta V sub C, the original one, divided by kappa. So that means that now the voltage that we're establishing is different, or the voltage that we had is different than the original one by a factor of this. This is before we're closing the switch again. So we just left it off.
Uh-huh.
It was an open switch. It was a charged capacitor.
Yeah.
The voltage changed
Yes.
by a certain factor, and that's actually kappa.
Okay.
So far, so good?
Yeah.
Okay, so I'm going to take one more step. And that is to say that we can actually describe this in terms of the capacitance. So capacitance is Q over, because I was going to write a statement and then I got distracted. Is that better? Sorry.
No,
It's a good thing you use pencil. You'd think that that's because this is the first time I've given these notes, but it's not. This is just how I give notes all the time. I get distracted, and yeah. So is that okay? That's just the definition of capacitance. So I can write this as Q over VC, the original one. Should write those as delta V's. I'd be a better person. Times kappa. Is that statement okay?
Yeah.
Okay. So then I can take this one step further and say that the new capacitance with the dielectric is equal to kappa times the capacitance in a vacuum.
Get why we make kappa the thing that why do we make kappa always greater than 1 rather than making it less than 1 by taking E over E naught?
It's arbitrary. I don't know. It depends on how you wanted to define it, right? So this I wanted to show you. So this is I just stole this from your book also. This is, of course, not something you would ever have to memorize, but just so that you're aware of what dielectric constants look like. So they're always going to be greater than 1, right? The dielectric constant of a vacuum is 1. Anything other than that is going to have a higher. Anything that is an insulator is going to have a higher dielectric constant, okay? And as a result, anytime you use a dielectric, the capacitance will increase, okay? Is that okay?
Yeah. I think
Okay. So now let me go back and see if I can fix that question that we were having before. If you look at the charge or the amount of energy that's stored in a capacitor, so I take that capacitor, the one that I had before, it was charged up, I have the dielectric in there. I'm going to close that circuit again. So now I've got my capacitor with my dielectric in there. It will charge up again to the voltage of the battery,
Yeah.
okay? But because I've increased my capacitance, I've increased the amount of energy that I've stored.
Okay.
Is that okay?
Yeah, yeah.
Okay. Is that sitting okay with everybody? Okay. Issues or questions right now? Okay. So the game is, as an engineer designing a circuit or designing a capacitor, you want to increase the amount of energy that it can store. And the ways that you do that are to put in a dielectric. And there are, like I said, lots of good choices for dielectrics. Some of them are more expensive than others, right? Here's paper right here. Okay? So it's 3.7. That's pretty good. A whole lot cheaper than glass or pure water or titanium dioxide, right? And so it is a good option for what we wanted in the camera. Okay? So you can do that. You can also, if we go...
How much would having ions in the water change the dielectric?
I think it'd pull it down, right? Because
Yeah, because then it would be a conductor.
yeah.
So then what's inside like electrolytic capacitors?
That I don't know. I mean, you could look it up. That's what I would do. So that's what I would do if I were you. The other things, so just kind of put this all back together. The other things that can affect the capacitance are the area and the distance between them. So if you think about the capacitors that were in the cameras, why did they roll them up like a cinnamon roll?
And you get the most area to overlap. While
Lots and
also-
lots and lots of area, right? Because that goes around and around, so it's like a bunch of areas it spins around. So lots and lots of area. And what do you want to do to the distance? You want to get it as close to each other as possible, right? Those are the ways to increase the amount of capacitance, which increases the amount of energy stored. That's from the book that looked pretty good, that kind of puts this all together. Oops. It's example 29.9. A 5, I don't think it was supposed to be micro. No, it's supposed to be nano. Excuse me. That's supposed to be an N. Nanofarad parallel plate capacitor. It's charged to 160 volts. It's then disconnected from the battery and immersed in distilled water. The kappa for water was, I don't remember, but we'll look it up unless somebody remembered.
4.6.
80?
Oh.
A little bit better than that.
Pyrex is 4.7.
It is that, okay, what is the capacitance and voltage of the water-filled capacitor? And how much energy is stored in the capacitor before and after its immersion? And then that last question is kind of a pulling it all back together, deeper question. I'll let you give that a shot, and then we can go through it if you have questions. So capacitance of the new one is equal to kappa times the capacitance of the original?
Yes.
Okay, so we need to find the capacitance of the original.
Yeah.
How do you find the capacitance of the original?
That's where it gets done.
Oh, okay.
Yeah.
Right there?
Is that what it is?
Yeah? Capacitance is measured in farads. So that should
Yeah,
be,
I think
that's
I
okay,
did
right?
last time. Okay, yeah.
Okay. And then to find the voltage for the new one, the voltage delta V sub C is going to be equal to the original delta V sub C divided by kappa.
No, because then they would multiply to
Did I
the
know
same
that?
charge.
Does that get you started?
Yeah.
Okay.
I think so.
What do we get for the capacitance?
400.
What?
Excuse you?
400 nanofarads? What'd you get for V? And then the energy initial? Oops. U sub C. Initial, you got what?
6.4 times 10 to the negative 5.
Units are?
Jowls.
Jowls.
Did your dad say that too?
No, I
Oh,
just,
you shouldn't then.
okay.
Because it's just not right and it sounds weird. I just don't want you to get that in your head. Like sometimes, you know, you start saying things because it's funny and then it gets stuck in your head and then it's bad. And then people look at you weird. We don't want that. All right.
Wait, hold
Um,
up. Hold up.
Sorry.
Did I type something in wrong?
I don't know. Do you square your voltage?
Is this your bad calculator?
No, it's my good one. I got it. So wait, 1/2 C. Okay, I don't even know what I did wrong. That's
1/2
wait,
of 5 times 10 to the negative 9 times 160 squared.
Oh, geez, that's what I did wrong.
Did you forget to square?
No.
Oh.
No. Let's not talk about what I did.
Okay.
Yeah.
And then for the other part, you got something like,
Yeah.
8 times 10 to the negative 7.
where does the energy go?
It goes for a second.
Wrong answer. This is a non-trivial question. Where does the energy go?
South for the winter.
Also wrong.
North for the summer.
I would not be shocked if I saw a question like this. This part is easy, right? Plug in, chug, and then you have the last part, part C of the free response question. Where does the energy go? What's your answer?
Converted on to
Oh, it went.
Think about what's going on. Where did the energy come from in the first place when we were charging the capacitor?
oh, the energy went back to
The electric field.
Where did it come from?
Oh, the battery.
It came from the battery. The battery had to do work on the capacitor. Does that make sense?
Yeah.
Okay. So that's not the answer for this. Darn it. But we're losing energy. So it stored a bunch of energy. You put the dielectric in and it's lost energy. We don't just lose energy to nothing.
in the dielectric.
What happened to the dielectric?
It got warmer.
It had an induced electric field.
Yeah, think about what happened to the little
The capacitor.
pieces of it, right?
The capacitor did work on the dielectric.
Yeah, the capacitor does work on the dielectric when it polarizes it. Okay? So in order to polarize the dielectric, work has to be done, right? It's not just going to like happen to do that. I mean, if you think about this in terms of like entropy, right? Like, it's not like it's going to be like, oh, I want to polarize. Sure. No, of course not. You have to do work to make that happen. And the work comes from the energy that was stored. Okay, does that make sense?
So what was that again? It goes into polarizing the. Yeah.
The capacitor
Yeah,
polarizes the dielectric,
Yeah.
and it does work in doing that.
Yeah. Okay.
Okay. All right. We good?